for organic chemistry. So the simple question is also okay. For example, if you don't know about DMAP or ACOH, what is ACOH? So you can ask and discuss in this classroom. And same with the with another SKO class. So this meeting, the students have been divided into 10 group, 10 groups. So each group, please ask and discuss at least one question to Prof. Zahir. So the in this morning, I'd like to start. The lecture series will be around 2 hours, and at the end of the meeting today, inshallah, Dr. Muhammad Ridwan as head of undergraduate program, or Dr. Asep Saifumillah as head of department will join our lecture, because this is the last meeting in this lecture series to officially close the UI Resolve program. So, okay. Honorable guest lecturer, Associate Professor Zahir Judeh, first will deliver the material, and then after that you can so not after that, while Prof. Zahir presenting the material, please note what the material, and please note which slide or which reaction you want to discuss. So please prepare well. And then the time is for question and answer discussion session. And then if we still have time, Prof. Zahir will give you little question for your exercise. Okay, without further ado, now I will give the time to Professor Zahir from NTU Singapore to present his lecture. So Prof. Zahir, the time is yours.
Thank you so much, Prof. Bayu. Thank you so much. And good morning to everyone. So today is our last lecture. And so before I give you the new material, I just would like to remind you with what we have discussed in the last lecture. So in the last lecture, what we did, we took some carbohydrates and we reacted them with malonitrile in the presence of an amine, and we are able to get these type of Pyrroles. And what we said these Pyrroles are very important because of the functionality here. At 2 and 3, you have an amino cyano Pyrrole. So these are important compounds because these compounds can be converted into many other compounds. You can make cyclic compounds of these. That's what we discussed in the last lecture. And I also gave you a question on how do you synthesize this compound. We have already discussed the solution for this compound, but I'm actually going to show you how we made this compound in the next slides. So you are able to connect what we are doing. So those of you who have watched the videos and those of you who are with us, we started our work by looking at the synthesis of unsubstituted Pyrroles. Then we looked at the substituted Pyrroles, and then we look at the substituted Pyrroles that has this functionality here. And today I'm going to talk to you about two other research areas or research topics that we have been doing for the last few months. So I'm going to talk to you about the synthesis of this compound here and the synthesis of these compounds. All right. If you look at the work that we have been discussing, and if you notice all the carbohydrates that we did and we investigated, these are aldoses, right? These are aldoses. So the question comes now, can we use ketoses like this? Can we use ketoses to do the same chemistry? That's what we are going to discuss here. So the application of the chemistry here is to investigate if ketoses can react the same fashion like aldoses. All right. And now, if ketoses can react the same way like aldoses, if this reaction is successful, ketoses are just like, if you look at this one here and you do this taumerism, then this is the closed chain and this is open chain. So this fructose here is something that looks like this one here, right? It is a keto, it's a keto alcohol. The question now is this: if fructose reacts like aldoses, can a general structure like this, any keto alcohol, can it react in the same fashion like fructose and aldose? This is what we are going to discuss. So are these two types of compounds, are they equivalent? Do they react like aldoses? That's what we are going to discuss in this work. So I'm going to start with investigation, the reaction of ketoses. Then I will do the application for these keto alcohols. So we took the simplest ketose, which is fructose, and react with this cyano compound, and in the presence of an amine. And we have investigated different types of catalysts, as you can see here. We have basically looked at Lewis acids, we looked at organic acids, we looked at bases, right? And then we investigated the reaction using ethanol and acetonitrile DMF. The reaction was carried out at 70 degrees. And then we are able to obtain this. If you look at entry number 10, the reaction is giving us with acetic acid 1 mole in DMF, 70 degrees, 76%. However, the most successful condition is number 1, in which we are using acetic acid in ethanol at 70 degrees and the yield is 77. There is no really difference between 76 and 77. However, we chose to do the reaction according to entry number 1 because ethanol is a much easier solvent to deal with in comparison to DMF. The reason is we are able to remove ethanol much quicker, much easier than DMF. DMF is a high boiling point solvent. So this reaction is really successful. It gives us the pyrrole that we are anticipating. Next, we wanted to understand if this reaction is a general reaction and can be applied to different types of active methylene compounds and different types of amines. So we examined the scope of this reaction. So we took first fructose and react this fructose with nitriles. So this R group here can be a phenyl or it can be a methyl group here. And reacted with different type of amines here, as you can see. So this is the type of amine we used here. Alkylamine. Again, this type of amine here. Look at this one here also. There are different types of amine because we wanted to see if this reaction really works very well. Naphthyl, ethylamine, cyclohexylamine here, and even here in this case here, aniline reacts very well, and substituted aniline also reacts very well. So all of these reactions are done with a phenyl substituent here. This reaction also works very well if you have a methyl substituent here. These are just to demonstrate that the reaction works very well. We also did the reaction using disaccharides, and we took isomaltulose, and the reaction proceeded very well, as you can see from these three examples, with this amine, this one here. Our group here is a phenyl, and our group here is a methyl. The reaction proceeded to give us acceptable yield, very good yields from 55 to 86% yield. And these yields are generally considered very well. As with the other compounds, these type of compounds are highly polar compounds. Their solubility in water is good. And we are able to obtain an X-ray structure of compound 1C, which is this one here, as you can see, just to prove the structure and understand how this structure looks like, right? So this reaction is really successful, and it gives us the same kind of products that we obtain in case of aldoses. So the other question that we will ask ourselves is, as I said, ketoses are just like hydroxyketone, right? So they are just like hydroxyketone. So we wanted to understand if hydroxyketone can react also to give us the products. So we took this hydroxyketone, we reacted this with the same type of nitriles. So our R group here is methyl, a phenyl, substituted phenyl with a chlorine, substituted phenyl with a methoxy group, and with a bromine. And we took different types of amines. The reaction proceeded under the same condition to give us 70 to 90% yield of the expected pyrrole. You can see the pyrrole here, right? And here, these different type of amines. All the way, and we are able to obtain the X-ray of 14C, which is this compound here. All right, it is important to understand that what is the difference between the previous compound and everything we discussed is that these type of pyrroles, they have this polyhydroxyalkyl chain. All the compounds have this, but now we are able to produce some chemistry in which we don't have the polyhydroxyalkyl chain. We have an aromatic ring here, right? We have an aromatic ring here. So this is a nice development. This is something that is really, really good. Now, I will later show you why did we develop this chemistry. Not just because we wanted to prove that these type of compounds can react like ketoses. No, the reason is we wanted to produce these types of compounds because they are important. I will later show you the application of these compounds in our work and how we synthesized these compounds. So next, we carried out this reaction at a large scale. We used 1.8 gram. In this case, we used 3.42. And in this case, we used 1.2 gram. So large scale works very well. It works with this type of nitriles and these amines, aromatic primary amines. This is primary amine. It works with mono sugars, disaccharides. Also, the yields are really good. And it also worked with this keto alcohols, as you can see in this type of example. So the reaction is kind of, this reaction is kind of wide scope, has a wide scope, and it is applicable on a smaller scale, large scale with different types of amines and with ketosis as well as keto alcohols. So we wanted also to do some kind of modification and understand if this structure can be modified. As we have done before, we were able to cleave this chain to bring it to the aldehyde group, and this aldehyde was reduced using sodium borohydride to give us the hydroxymethyl pyrrole, and the yield is very good. All right. When we looked at the chemistry, based on our understanding, based on the mechanism that we have discussed before, and based on the experiments we have provided to give us evidence for the mechanism that we have discussed before from our previous work, in this type of chemistry, we propose 3 different paths by which the mechanism can proceed. So if we look at path 1, path A here, so I have the hydroxy ketone. So this hydroxy ketone could be really coming from the hydroxy ketone itself here, or it could be coming from the disaccharide, or it could be coming from the monosaccharide. Remember that this is basically this one here, right? So we have the same kind of arrangement here. So this is a keto alcohol. This is also keto alcohol. So here's our keto alcohol, as you can see here. And this keto alcohol, initially it reacts with the amine to give you this Schiff base, as you can see here. So this is under acidic condition. Dehydration takes place to give us this imine or the Schiff base, and then this isomerizes to give us the keto isomer. So this can this will react with the acid. You get an acid here. This nitrogen becomes positively charged, and then this will move here, and you will get the keto. You will get the enol first, and from the enol, you will get the keto form, as you can see here. So this is something that we have shown before when we talked about the mechanism for the previous reactions. Now, once we get this, it will react with the nitrile here, and this reaction here is a very simple reaction. It gives us this intermediate. All right, the intermediate now. So the reaction happens at this. The reaction happens at this carbon here. So you have linking the nitrogen with the carbon. This is the nitrogen. This is our carbon here, and then the next step here. Again, these electrons move here, and these electrons react on the electrophilic carbon to give us this cyclic intermediate. This cyclic intermediate undergoes aromatization to form the aromatic ring here, which is very stable, to give us our product. So this is path A. Path B, now the reaction happens between the amine and the nitrile. So instead of the amine and the keto alcohol, the reaction can happen between the amine and the nitrile. So in this case here, we have, so this reaction here results in the formation of this intermediate here, and then electrons move here. This reacts, this is a nucleophilic, it reacts on the electrophilic center here, kicking out electrons in the oxygen, and you get the intermediate here. Then what you do is you lose this proton here, the electrons move here, these electrons go here between the 2 carbons, and then these electrons move on top of the nitrogen. All right, nitrogen becomes minus, it takes a proton, and here is our proton. The next step is you have intramolecular attack of the nucleophile to the electrophilic carbon, kicking out electrons on the oxygen, and you get this cyclic intermediate. Same thing, this cyclic intermediate, like the one we have seen here, it will re-aromatize to form the aromatic ring and give us the product. If you followed the previous work that I presented, we had sequence 1 and we had sequence 2. All right, In sequence 1, I'm reacting this aldehyde with the amine, and then I am adding our nitrile. In sequence 2, I'm reacting the amine with the nitrile, then I'm adding the aldehyde. So these are the two sequences. Both of these sequences, as you can see, give us the same product. All right. In this reaction, we did not observe two products. In this reaction, what we observed is only one product. Therefore, there was no sequence 1 and there was no sequence 2. So both sequence 1 and sequence 2 could be operating in this reaction. We did not separate any intermediate compounds. So both of them could be separating, and that's why the proposed mechanism is shown to you here. Right. There is another mechanism in which we are reacting our nitrile with the hydroxy ketone. Our nitrile with the hydroxy ketone. This is a nucleophile. If you remove the proton from here, this becomes C minus. All right. So C minus here is going to react on this carbon here. So nucleophile, electrophile, it gives us this intermediate. All right. This intermediate now reacts with the amine. Okay. And the amine can react on this. The amine can react on this carbon here, kicking out electrons on the oxygen here. It becomes an OH, and it will give us this intermediate. All right. The intermediate here now, this proton here is acidic proton. The base take the proton, electrons move here. These electrons go here, and these electrons go on top of the nitrogen, and then nitrogen becomes N minus. It takes a proton, it becomes NH, as you can see here. All right. Now, this will react to give us the product here. How does this react? This react in such a way that it is actually, so it will form the keto form. This is the enol form. It will undergo diatomerization to form the keto form, and then the keto form will react, in which case the nitrogen will react on the carbonyl carbon here once the keto form is formed. So these are the possible mechanisms that are operating to give us the product. All of these mechanisms are possible, and they are able to give us the product. So we think that maybe path A or path B is actually the most likely scenario in this case. All right. So to summarize this work, what we did is simple. So we took the nitrile and the amine, we mix them together, in one case with the ketosis, with the fructose, to give us the required or the anticipated pyrrole. In other case, we took a general hydroxyketone, and the reaction proceeded to give us this type of pyrroles. The main difference between these two pyrroles is we have an aromatic ring here, and this we have a polyhydroxy chain here. These two are versatile products. Okay, so this summarizes the first piece of work that we have done. And now I am going to talk to you about the last piece of work before I talk to you about the application. So in this case here, what we are doing, we are reacting the nitrile with the amine in the presence of these types of compound. These types of compounds are basically hydroxyketone. I will show you what I mean. So this type of chemistry, if you look at this one, this is, now we can say that this is tetrahydroindole. Tetrahydroindole. So these indoles are very important intermediates, or very important products in chemistry. Synthesis of these tetrahydroindoles is important. And if you look in the literature, we have this type of research that has been done and published using to produce tetrahydroindoles here, and here, and here, and also here. So if you look at this type of chemistry, you have a nitrile that reacts with amino ketone to give you the intermediate, and then this intermediate, you cleave out this to give you the product. If you look at this second one here, you have an epoxide, reacts with alkynes in the presence of a very strong base to give us this intermediate. And now this intermediate is converted to the nitrile. If you look at this chemistry here, you have amino alcohol reacting with activated 1,3-diketone to give us this intermediate. And this intermediate can be converted to the tetrahydroindole. In the last piece of work here that was published, if you look at this work here, you have again a diketone similar to this. These two are similar, 1,3-diketone. And the first step is the formation of the furane, right? You can see that this is the ring. This is the oxygen here. Then the furane is converted at high temperature to the indole, and then reduction of this carbonyl group give us the indole. If you notice, all right, this type of chemistry here uses complex structures, and it is also a multiple step. So here, 1, 2 steps here, 1, 2 steps here. This is 1 and 2 and 3 steps here to get this type of tetrahydroindoles. You also sometimes require high temperature. You require very strong kind of reagents, and sometimes you require the use of other substrates that you have to purchase. So when we look at this chemistry, we decided that, okay, maybe for us, it makes sense to try and use our chemistry that we have discovered to obtain this type of pyrroles. So this is what we did. We took this compound here. This is a dimer, and this dimer is actually the same thing like hydroxy ketone, right? This is our cyclic hydroxy ketone. All right. I just want to remind you with this idea here. This is a hydroxy ketone. This is also hydroxy ketone. But this hydroxy ketone here, it gives us an open chain here. Now, what we wanted to do, we wanted to go and make tetrahydroindoles, and therefore we have to use cyclic structures. And this is where we use, which is actually, it comes in the bottle in a form of dimer, right? Now, we took this and reacted it with the nitrile in the presence of an amine, and we are able to obtain the tetrahydroindole in really high yield and in just one step, all right? After trying different type of catalysts, all right, as you can see here, and ethanol at 70 degrees for 5 hours, entry number 8 is the best reaction condition. Using 0.5 molar triethylamine, it gives us 77% yield of this type of tetrahydroindole. So we can say that this chemistry is simple, it's one step, the yield is good, and the temperature is not so high, yeah. And ethanol is a nice solvent. Triethylamine is a cheap, very cheap catalyst, and we don't have a problem of using this catalyst. So we wanted to understand if this type of chemistry is general, all right, if it is general, and if this type of chemistry can be actually it can be applied to other kind of compounds and amines and nitrile. So we went on to check the scope of this chemistry. That is the next step. So if you look here, we took our hydroxy ketone, we took this nitrile, all right? This nitrile here, the R1 group here, it can be a methyl, it can be a phenyl, it can be substituted phenyl with a fluorine, substituted phenyl with methoxy, or substituted phenyl with a chlorine. And we took different types of amines. This reaction proceeds very well in just 5 hours to give us 68 to 92% of the intended tetrahydroindole. All right. If you look at the details of these examples, you will find a long chain amine. You find cyclopropylamine, cyclobutylamine, cyclobentylamine, and you find also cyclohexylamine. All of these react very well. You find an alkyne, a benzyl, naphthyl, and you find this type of amine. Now we're having a substituent here, or here, or here. And then you find aniline also react very well. This is important to show. And now instead of using phenyl, our substituted phenyl, we are using here a methyl group to demonstrate that this type of chemistry can be used with different types of nitriles. All right, so this was really a good result for us because we are able to obtain tetrahydroindoles in just one step with different types of amines, different types of nitriles, and the yield is really excellent. So I don't have to really go and make two-step reaction and maybe heating at 150 in DMF or using this 150 degrees here, deal with different acids, or using very strong base like butyl lithium. Your reaction has to be dry. Everything has to be under inert atmosphere because butyl lithium is very reactive base. If it comes in contact with water, it will really give you a fire. It will explode. So our reaction is really simple. The application is simple, and it also has a wide scope applicability, as you can see here. All right. Now we did this reaction also on larger scale, and we demonstrated this scale using 1.4 gram of our starting hydroxy ketone, 5 millimole, as you can see here, with this nitrile, this amine, primary amine. Here is using our secondary amine with this nitrile. We are using here the primary amine with this nitrile, and we are using a secondary amine with this nitrile. All of these are just to demonstrate that this reaction can be done at large scale. You can see that the yields are really good, over 70% yield for all of these structure. So to summarize this, we are able to do the reaction with a wide scope, and the reaction can be done on large scale. All right. Now, the question becomes here, can I make indole, right? So the next step is very simple for us. If you take our tetrahydroindole using DDQ, all right, you are able to obtain this type of indole. So I have an aromatic ring here. It's not anymore tetrahydroindole. It's a full indole structure. The reaction is very simple. You take the starting material and DDQ here, and then in the presence of solvent, your solvent is dioxane, you reflux, and you are able to get the product here. Likewise here, you are able to get the product here. So DDQ is an oxidizing reagent. It oxidizes this ring to give you the fully aromatic indole here. And this is our X-ray structure of this, and this is this one here. Interestingly, we are also able to obtain the X-ray structure of this type of indole, indole 5, in which we have a cyclopropyl ring, as you can see here. Okay. Now I will come to the last piece of this work, which is really application of this work. So you notice that we have not spoken about application so far, and all we did is to develop the chemistry, developing our chemistry so that we are able to understand the mechanism of the reaction, the scope of the reaction, where its applicability, and in order for us to widen the scope, we thought, okay, it must be easy for us to try to apply our chemistry to synthesize drugs or drug intermediate. So this is an NSAID, non-steroidal anti-inflammatory drug. This is present in the market, and these are lead compounds as anti-tuberculosis compound. So in our application, we thought, let us try and develop a synthetic way to obtain these compounds. So when we were looking in the literature, we found that these compounds can be synthesized as follows. So this is a previous synthesis of NSAID, which is published in this journal. So the steps, as you can see here, there are so many steps that are involved in the formation of this compound here. All right, there are 6 steps to obtain the compound here. All right, now this type of anti-tuberculosis compounds labeled as BM212, 521, and 533, they are very similar. All right, they have the basic structure. The basic structure is here, all of this. So these compounds, they differ in the R group, and they differ also in the X. X can be nitrogen or it can be sulfur. Therefore, for us, we need to develop the synthesis of the core structure, and then this can be attached to the core structure, right? This is what we have to develop. So in the literature, these type of compounds can be or are synthesized as follows. You take this bromoketone with a diketone here, and you obtain this intermediate, and this intermediate can be cyclized to obtain this compound. The ester is reduced to the carboxylic acid, and then this carboxylic acid react to form the morpholine type ring here, as you can see in this compound here. And then this carbonyl group here is reduced to the methionine group here. So you can see that there are 5 steps in this product. So when we looked at all of this, we thought, okay, can we somehow use our chemistry to synthesize these compounds? What can we develop in this chemistry? So this is what we did. First, I'm going to talk about the synthesis of this compound here. As I said, this is done in 6 steps. And for us, it was really very simple. So the synthesis of this compound is mentioned in this line here. We can do the synthesis in just 1 step. So if we take our hydroxyketone, we take our amine, which is aniline here, we take our nitrile, mixing these together give us the NSAID in 53% yield in just 1 step. So we have really done a major improvement in the synthesis of this compound. All right, doing this chemistry, following this chemistry, we can also make analogs of this compound. All right, with this chemistry, you can really make, I think you can make hundreds of compounds, all right, by changing the aromatic ring here, the substitution at the aromatic ring, or here, or here, or the nitrile group. So we demonstrated that this reaction can also be done to make analogs like this one here and like this one here. All you need here is to mix the right amine with the nitrile to give you the product. And this product was obtained in 76% yield and 78% yield. So this is a major improvement on the literature synthesis of this NSAID. Right, I'm going to look next on the synthesis of BM212. Right, for the synthesis of BM12, the structure really is the same. The basic chemistry is the same. So we took the hydroxyketone, we took an aniline, and we took the nitrile. We mix them together in 1 step, and we are able to obtain 60% of this. This one is the basic framework to obtain BM212. Now, if you change the chlorine to a fluorine here, and you do the same chemistry, you will obtain the framework that is used to obtain BM521. Again, if you use this type of hydroxyketone, in which I have a methoxy group here, a fluorine here, and react them together, you are able to obtain the framework that is used to obtain BM522. As long as you made the framework, the next step should be really simple. So what are the next steps? I'm going to highlight the synthesis of this one to show you that our chemistry really works to obtain the final product. All right. So we carried out this reaction and we obtained this structure here. This structure is now shown to you here, the same structure, 15. Next step, what we did is we did a reduction of the nitrile. If you use a dival to reduce nitrile, you are able to obtain the aldehyde. Reaction of aldehyde with this amine, you get the Schiff base. There's a double bond, and this can be reduced with sodium borohydride. This is a one-step reaction to obtain this product. So instead of doing this over 5 steps with a little bit of somehow difficult chemistry, we are able to obtain this in just 1, then 2, and then 3 steps. And if you look here, these yields are really high, 95, 93, and here is 60%. If you look at the literature here, the yields are 73, 84, 92, and this is 100%, and this is 85. All right. So what we did, we actually demonstrated that our chemistry can be applied to obtain these compounds in much shorter steps with excellent yields. Here, I'm just showing you the X-ray structure of the final product here. Okay, so to conclude all my work and all the lectures that I have given, this slide really gives you a conclusion of what we have done. So we took different types of carbohydrates, all right? The first work we did is we reacted the carbohydrate with nitrile in the presence of ammonium acetate. We are able to obtain unsubstituted pyrroles, all right? The next work we did, we took the carbohydrates with the nitriles, alkylamine or arylamine. In the presence of these type of catalyst, you are able to obtain differently substituted pyrroles. And these are substituted pyrrole here, and this is your 2, 3, and 5. This is your 2, 3, and 4 substituted pyrrole. In the other piece of work that we did, we were able to obtain the 2, 3, 4 pyrrole in which the substituents here are amino nitrile, which are used to actually obtain different cyclic structures. And today's work, we looked at the chemistry of having this nitrile and the amine to react with hydroxyketone to give us this type of tetrahydroindoles. And we said that the tetrahydroindoles can be converted to indole. This is the latest work that we are doing. So this work has not been published yet. And the other piece of work we did is we did the same reaction or similar reaction. We took the nitrile with the amines, and we took now ketosis, not aldoses. We took ketosis. We are able to obtain the same type of pyrroles. We also extended the work not just to carbohydrates, but hydroxyketone in general to give us this type of pyrroles. Okay, now it is question time. I can see Rossi.
Yes, sir. Good morning, Professor Bayu and Professor Zahir. My name is Dia from Group 5, and I want to ask about your presentation about the mechanism in path C. In this path, you say the nucleophile is a minus, and my question is, why not the oxygen will be the nucleophile who has more electrons? What is the reason about that, sir?
Rosik, your voice is not so clear. Can you please repeat the question? So you're asking about this slide, the mechanism, right?
Yes, sir.
Okay, good.
Is it better, sir?
Yes, that's very good.
Okay. My question is, in Patsy, you said the nucleophile is a C minus, and my question is, why not the oxygen will be the nucleophile who has more electron? And what is the reason about that, sir? Thank you.
No, there are two acidic protons here. There's one here and there's one here, right? There are two acidic protons here. One here and one here.
Yes.
So this methylene group is called active methylene. Why is it active methylene? Because the two protons are very acidic protons. What you have here is lone pair of electrons, right? So once a proton is removed, you have C minus. C minus has a formal negative charge. This formal negative charge is much stronger in nucleophile in comparison to OH. And therefore, this will be the nucleophile that reacts on the electrophilic carbon. All right?
Yes, sir.
Yeah. So, Ross, we know that. So in the absence of this, so if I don't have this methylene, active methylene, can OH, can alcohol react on this carbon? Yes, it can. Yes, it can. But because this is present, this is a better nucleophile than the OH. So there's a competition here. Which one is a better nucleophile? So this is a better nucleophile than this one. Am I clear?
Okay, thank you, sir.
Okay. Paras?
Okay, is that my sound is clear?
Yep.
Okay, thank you for the opportunity. My name is Faras from Group 5 Synthesis of Organic Chemistry. I want to ask for page 68, this page, about mechanistic study. It says there are 3 paths to make products. Which path is most preferred? Thank you.
Right, thank you. This is a very good question. So as I said, so based on our experience, right? If you have watched our videos before, you will see that we have sequence 1 and sequence 2. So assume that this is sequence 1, this is sequence 1, and this is sequence 2. So both of these takes place. To be honest, I'm not able to tell you which one is really the one that is operating under these conditions. We have not really investigated. We have not really isolated any intermediate. All right. So I will not be able to tell you which one is the one that is really operating under these conditions. All right. But what I can say, so when we mix our fructose with the nitrile, with the amine, when we mix all of these things together, we don't do it in sequence. We mix everything and we heat up the reaction for the specific time under this temperature. All right. We have not really studied the mechanism using some kind of experiments like we did before, like using NMR or using mass spectroscopy. We didn't do that. Therefore, I cannot tell you which one is really the one that is most likely to happen.
Okay, thank you, sir.
Okay, Vanessa.
Vanessa. Vanessa.
Hi, am I audible?
Yes, Vanessa, sorry.
Okay, so thank you, Professor Zahir, for the lecture. I have one lingering question, that is, why exactly that phenol substituent is much more better substituent in comparison to methyl, as it gives off better yield for the synthesis purposes? Thank you.
So, Vanessa, your observation is really good. And I think because we are able to purify the product much better, much easier, because this type, when you have the phenyl, the structure or the compound become less polar. So the polarity is low, and therefore the purification is easy. And I think this increases our yield.
Oh, I think that, and that clears the answer about having much more yield and able to have faster results. So thank you so much,
Yeah.
Professor.
Also during the reaction, carbohydrates are known to decompose a little bit. Yeah, especially when you heat the reaction. So if you look at our reaction, when we start heating the reaction give us a black color, dark yellow or a black color. This indicates decomposition. So when we have this phenyl, instead, we are able to obtain that the dark color becomes a little bit faint. Therefore, you would think that, oh, there isn't much decomposition. So it's a combination of two, basically.
Okay, that answers a lot, Professor. Thank you so
Thank
much
you.
for the
Yeah.
explanation.
Muhammad Fathul.
Good morning, Professor. Uh, my question is around the synthesis of the, if I'm not wrong, the NSID.
Yes.
Yeah. Oh, this part, around this part, there, maybe after this or before this, there's the few pathways of synthesis. I forgot where.
Are you talking about this one?
Before this.
This?
Before again, I guess. Once more.
So let me, this one?
Yeah.
This one?
That one, yeah.
Okay.
So maybe from a retrosynthetic standpoint, we often find the simplest precursor, right? So for this kind of reaction where there is one or more, two or more precursor, can we just take one of the precursor as the main precursor, or do we need to make like do we need to put in all three precursors and then the reagent maybe?
So this is Muhammad, this is a one pot reaction. So this is a one pot reaction. What you will do is you mix everything together and add a little bit of acetic acid and then heat the reaction. You get the product. Did I get your question right, or?
So can we not? So if I were to do retrosynthetic something, can I not do it because there is only one step, or?
Of course, you need to. I mean, if you look at this structure, right? So this is our target compound, right?
Yes.
So if you do retrosynthesis, you will need the three things. Yes, you will need an amine. This is our amine. You need a nitrile. This is our nitrile. Yes, and you need the carbohydrate. This is our carbohydrate. So you need this. Likewise, here, this is your nitrile. This is amine. And this is, all of this is your carbohydrate,
Okay.
right? So this is how you do retrosynthesis for this type of chemistry. Yep.
Oh, so because this is only one step of reaction,
Right.
can I just put like all three precursor in the?
Yes. Yes.
Oh yeah.
Yes. Yes.
Okay.
Of course. Yes. 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 So once you decide
Okay.
on,
Thank you, Professor.
yeah, once you decide on what are, so if you do retrosynthesis and you decide on, okay, this is 1, this is 2, this is 3, and then you can mix them together, and then you can obtain the product.
Okay. Thank you, Professor, for the answers.
Thank you. Ashifa.
Thank you, sir, for the presentation. My name is Ashifa Salia Arif from Synthesis Kimia Organic B from Group 7. I want to ask, in the table of page 72 about tetrahydroindoles from hydroxyketones, why we have to use a temperature of 70 degrees? Is it because of its stability at 70 degrees or something else? Thank you.
Right. So Ashifa, if you look at this, you have an entry here of 50 degrees, right? So 50 degrees give you 42%. So 70 is required to speed up the reaction and increase the yield. Yep. So that's why 70 degrees is needed. We cannot use, we tried to use higher temperature, but then we are not able to get better yield, because at that time when you use higher temperature, you get more decomposition of product. The reaction mixture becomes really black, which is not good. Ashif, did I answer your question, Ashifa? Is that clear?
Yes, it's clear. Thank you, sir, for the
Very
answer.
good. Thank you. So the optimum temperature is required to get the optimum yield. And the optimum yield here is 77. If you use lower temperature, your yield becomes really low, 42.
Okay, thank you, sir.
Thank you. Lanabila.
Okay, thank you, sir. So my name is Lana Bila Salma Anjania from Group 9, a student at Universitas Indonesia from class SKB. So my question is probably probably a little bit out of topic, and I forgot which page, but I think it is in page 75 that explains that DDK can convert from tetrahydroindoles to indoles. So my question is, why can the DDK with dioxane easily convert tetrahydroindoles to indoles? And is there any reason to it, like a mechanism or something? Thank you, sir.
So DDQ is used to is an oxidizing reagent. So it's an oxidizing reagent. It oxidizes these types of ring to remove hydrogens. Okay. Once we remove the hydrogens, we are able to get this aromatic compound. So it is an oxidizing reagent. Okay. DDQ, if I remember the structure, is I think it is this one here. I don't know if this is a chlorine or a methyl group. I can't remember exactly, but one of them. I think it's probably a chlorine or, yeah. So it's an oxidizing reagent. It removes the hydrogen to give you the aromatic ring.
Thank you, sir.
All right, Chawla.
Okay, sir. Thank you for the opportunity. My name is Aula here from Group 1, class SKOV. I want to ask about the same thing from Lana Bila. So this is about the reagent that can convert tetrahydroindoles to indoles. So Is there any reagent that work like DDQ reagent?
Wow. Okay. The only reagent we tried is DDQ because it's very successful. It's very easy to deal with. It doesn't require any kind of special conditions. So you can just have the reaction open to air. It doesn't matter. It doesn't have any metal, so we don't have to. And also, its purification is easy. That's why we use DDQ. Yeah, we didn't try anything else, Chawla.
Okay. Thank you, Professor.
Okay. Rahmadia.
Okay. Good morning, Prof. Zahir. I'm Rahmadia from Group 2. I want to ask about the scope of the reaction scheme. There it is written that alkyl 1, 2, and 3 can be replaced. For example, alkyl 1 can be replaced by hydrogen or methyl, and and in the reaction scheme, it produces a yield range of 70 to 90%. I want to ask that the type of alkyl does it affect the yield, and if it's so, how does it affect it?
So what slide are we referring to? Are we referring to this one, the scope reaction here? So I can't hear you now.
Yes, sir. Yes.
So we are referring to this slide?
Yes, sir.
Okay, so what is the question again? Sorry, I didn't catch you.
The type of alkyl does it affect the yield, and if it's so, how does it affect it?
So, all right. You mean the type of amine? Are we talking about this one here? The alkyl chain here? Are we talking about that? Are we talking about yes? Okay.
Yeah.
So right. Okay. If you notice one thing, for example, you will notice the following, that if I have a primary amine, the yield is generally higher in comparison to secondary amine, right? And it is also higher than tertiary amine, secondary aromatic amine. So primary, very high yield, then a little bit lower on secondary amine, and a little bit lower if your amine is aromatic. I think this is related to the basicity of the amine. We know that the primary amine, like this one here, right? This is the most basic. Comparison with this lower basicity, and this one is the lowest basicity. This type of amine is the lowest basicity because your lone pair on the nitrogen is busy in resonance, right? So they are not really very available to be donated as much as if you have a primary amine. So I can say that the yield really depends on the type of amine that you use. If the amine is more basic, then the yield is better. This is in general, yeah. This is one observation. The other observation is the following. Reactions with fructose gives you better yield in comparison to isomaltulose. So if you compare the yield of this is 86, same amine gives you 68. This is coming from glucose, while this one is coming from isomaltulose. So this is a lower yield. This is also a lower yield. All right. This is because I am using here disaccharides. Does that explain the answer to you?
Okay, thank you, Prof.
Thank you. We have Alexandra next.
Okay, hi Professor. Thank you for explaining the new knowledge. I would like to ask about the mechanistic studies, the ones with the three paths. Yes, this one. Okay, so you've mentioned that all three paths are um, reacting and like producing only one product. I'm curious, is there any perhaps like one of the three paths are the most like path to like react? So like the product apa ya? Which one of the three paths are
Okay.
like the most liked path
Right.
for to,
Okay.
yeah.
Good, Alexandra. I think we answered this question before. So my answer to this question before, I can't really tell you which one is the most or most probable path. All right. So all of these paths are possible. We have not really done experiments to kind of show what are the intermediates. So we didn't do these experiments. In fact, if you look at the intermediates are I didn't really check exactly, but the intermediates here, they have the same mass or very similar mass. Reason is that because we are in all of these cases, what we are only doing, we are just removing water. All right, we are just removing water. You can see water here. We are just removing water here. All right, we are just removing water here. So all of this will have the same mass. So it's very difficult to distinguish which path is the most operating one. All right. So I couldn't really tell you. I think the student who did this work, she tried to do the NMR after 20 minutes, but she obtained a big mess. So once you obtain a big mess, it means that you have so many intermediates. And this is not, there's no clarity in your NMR. It means that all of these paths are probably taking place at the same time. And if you look at the mechanism, you know, all these type of mechanism, all the mechanism mentioned here, they make sense, and you know, they're acceptable mechanism. If you look at the work that we have done before, you will see that path A is possible, and we have evidence for that. Path B is also possible. We have evidence for that. And path C is really, you know, it's also possible, but we didn't really obtain any evidence from spectroscopic studies, or whether NMR spectroscopy or mass spectroscopy. So in short, all of these paths are possible. They have we have evidence for all of them operating from a previous work. In this work here, the first NMR for the first 20 minutes gave us a big mess. So we concluded that probably all of these paths are taking place at the same time.
Okay, thank you, Professor.
All right, thank you. Nadifa?
Okay, thank you, sir, for the explanation. My name is Nadifa. I'm from University of Indonesia, SKOB class, and I'm from Group 9. I want to ask, what is the factors affect the yield of reactions that prevent them from achieving 100% yield? Thank you, sir.
Wow, Nadifa, your name has an importance to your question. Yes. So you want 100% clean reaction. Okay. So this if you look at the chemistry using carbohydrates, all right, as long as heat is involved in this chemistry, you will always get decomposition of products. It is extremely difficult to get 100% yield of this type of chemistry. So this is one reason. Carbohydrates are known to have decomposition of products. So this is a possibility. The other possibility is that we are doing reactions under really very small what is it? The starting material is very little. The scale is very small scale. So we are using 0.2 gram, 0.3 gram. So this is what we are doing chemistry on. So if you are doing chemistry on a small scale, then you have losses that are due to working, maybe extraction, maybe working, and you have losses during to chromatography. It's possibility. So when you also transfer material, you also have losses. So I think the possibility of not getting 100% yield is coming from the use of carbohydrate. The reaction is not so efficient to give you 100% yield, and maybe because of the person who's doing this work is a little bit losing material, whether it is in a purification or whether it's in kind of transferring material from one flask to another flask. Yes. Nadifa, is that do you have any other question? Is that
Okay, sir. Thank you so much.
thank you. So I got Risky.
Yes, Prof. I would like to ask the question about the DDQ oxidizing agent, as in the step of oxidizing tetrahydroindoles into indoles.
Yes.
Yes, yeah. As we can see from the picture here, the DDQ will oxidize the cyclohexanes that connected to the pyrroles to the benzene, but why does it not oxidize the cyclohexanes that comes from the amine?
I think it's because this has, so this ring here, to start with, this ring is aromatic ring. Okay, this ring is aromatic ring. This ring is connected directly to this ring. So the oxidation of this ring is much easier than this ring here, because the product that you form here is very stable. So you know that aromatization is a stabilizing factor, right? So when we do this kind of oxidation, we are actually making a more stable product because the product is aromatic. Okay, in this ring here, this ring, there's a bond between this ring here and this ring here. That's why this ring is not really oxidized to form to be aromatic. So because of the aromaticity here, this already have a double bond here, right? So this becomes aromatic easy.
Okay, Prof. So that the reason why the cyclohexane that connected to the indole becomes benzene ring is just because it's more easier to oxidize than the cyclohexane one.
That's right. That's correct.
Okay, thank you very much for the answer, Prof.
Okay. So next we have Venice.
Yes, sir. Thank you for the lecture. I'm Vanas from Group 1 SKOB. I wanna ask, is there possible the product give mixture product or like chain of product isomer? If that happens, I will change the properties or attribute of the product.
Venice, can you please ask the question again? I couldn't hear you very well.
I wanna ask, is there possible the product give the mixture product like chain of isomer?
Oh, so you mean this? Okay, I got what you say. All right, let's take, for example, this one. So you are saying that is it possible that this gets isomerized in the reaction, or we get different isomers? It's not possible. Yeah, it's not possible. So the reason why it's not possible is that because we are starting with fructose, right? We are starting with the fructose. So the stereochemistry at these centers is fixed. we are not playing with the stereochemistry here. We did not touch the stereochemistry here. And under the conditions that we are using, there's no isomerization of the centers here. So there's nothing that can remove the proton here, and then the proton comes back. No, we are not doing that. So there's no isomerization, and we have not observed any mixtures of products. Yes. If you notice, let me go back here. So if you have watched the the previous lecture, we said that in the beginning of the reaction, when you take a glucose, right, you will have alpha D-glucose and you have beta D-glucose. So the material you buy, it comes with a mixture of alpha and beta in the bottle, right? It comes as alpha and beta. Now, when you do this reaction, so alpha and beta is only at this center here. It's only at this center here. And you know that for our type of chemistry, this center here will open up. So these electrons on the oxygen here, these electrons will move here, all right? And now this one opens up, all right? When electrons are moved here, you get the double bond to the oxygen. You get the carbonyl group. And this becomes a chain, right? So this chain, this becomes like that. All right? We open up, but that one is aldehyde, this is ketone. So we get the keto group, exactly what we get here. So these centers here and here and here and here, they are not involved in the reaction. Therefore, under the condition we use, they are not really isomerized. Okay, so this is the center that we deal with, our reaction center here. And you can see that from the NMR, you have the alpha and you have the beta anomer. And as the reaction proceeds, you can see this is decreasing, decreasing, and decreasing, and decreasing. And here is almost lost. A little bit here, there is a little bit here. But as we go, we don't have this, right? It's gone. So there's no isomerization.
Okay, thank you, sir.
Thank you. Christopher?
Okay, thank you, Professor. My name is Christopher. I'm from Group 10, Class B. Okay, I would like to ask you something from the page 77. Okay, so I would like to ask you something about the left side. There is, I believe it's some kind of benzaldehyde derivative, and we do some type of conjugate addition with some type of, I believe it's some kind like acrylane derivative. But I'm curious how it's that reaction possible. Like we see that the benzaldehyde does not have an alpha proton, and it can be inolate to react with conjugate addition. So how do we obtain the product from this reagent? Thank you.
All right, good. So, Christopher, this is a very good question, and I am not going to give you the answer, but I'm going to help you with the answer. Okay, so look at this. Is this so? If you do kind of what do you do? If you do a kind of resonance, right? So if you look at this double bond here, right, and you do resonance, what we have here, we have this bond here, right? This is the bond. This is the new bond that is formed, and this new bond here, it's formed from this carbon here to this carbon here, right? This is the bond that is formed. Am I correct? So it means that I'm actually doing this kind of chemistry here. Am I correct? So how will this chemistry happen? What do you do in order to observe this chemistry? That
I think
means,
we can do some kind of reverse polarity chemistry, sir.
yes.
Like we convert to the aldehyde group to the ketal group, the thioketal group, I think, and then we do some kind of conjugate addition. Is that possible?
All right. So, Christopher.
Yes.
Yes, good. How about this? This is a very interesting question. How about this? You try this mechanism with your group and email me the answer.
Okay, so I'll try with my group. Thank you.
Yes, and email me the answer.
Okay. But some little question. How about the other reagent that can I use? Can I use freely or you
Yes.
decide the
Yes.
reagent?
So please record this. So record this one. So this is our reference that you need to refer to.
Okay, sir.
Record this, and for the mechanism, you do it with your group, email it to me, and I will email you.
Okay, sir. Thank you.
Good. So we have Salsabila.
Okay, Prof. Zahir, thank you for the opportunity. My name is Salsabila Freya from Group 8, and I want to ask you about the large-scale reaction. Okay, like how can we know the ratio of the scale to produce the reactant, sir?
Oh, all right, Salsabila. So for us, we are using reactions. So our reaction always we use 1 millimole. All right. So we start from 1 millimole. All right. And then the student decided that, okay, I want to go from 1 to 5 millimole. All right. So if you are doing process chemistry, and you want to scale up the reaction, they say you double your reaction. So if you are using 1 mole, you go for 2. And if you are using 2, you go for 4. This is how you double the scale. All right. Because this chemistry is a little bit easy for the student, and the student has been doing this chemistry the entire of her PhD, she went from 1 gram to 5 gram. And so she is able to do this kind of chemistry. And we didn't want to go for over 5 millimole because we don't have much of this material. Yeah, we just want to conserve our material. The fact that this chemistry worked directly from 1 millimole to 5 millimole, and it gives you a very high yield, it means the chemistry can work on larger scale. And you have no problem scaling up the chemistry. So here we wanted to demonstrate that we don't have a problem to scale the chemistry, and we can jump from 1 millimole to 5 millimole directly without any problem. Yeah. Can you make 10 millimole, 20 millimole? We believe you can make easily, and you won't have any problem. That's the gist of this.
Okay, thank you so much, sir.
Thank you. We have Tiara.
Okay, thank you, sir. My name is Tiara Delina from Organic Chemistry Synthesis Class B, Group 3. My question is, in mechanistic studies, as you can see that there are 3 different steps, but it will be one product. There are any side products, and what affects it? Maybe temperature or pressure or something else, sir?
Right. So we don't have any side products here. So we don't have any side products. The only thing we get is this product. The side products are basically decomposition of products. So when we are doing the chromatography, as I said, there's some black material. So this material, when you do the chromatography, it will stick to the silicon. Yeah, we don't have any other products that comes from the column. So this is the only product that comes from the reaction. The rest of the material is a black material decomposition product that sticks to the silica and doesn't come out. So we don't know what it is. It could be char. Yes.
I see. Thank you, sir.
Okay, thank you. Okay, we have Anida. Anida, your mic is... Should we go to Kahya and then come back to Anida?
Okay, I think I will go first. So my name is Chahya. I'm from SKOB Group 9. So maybe my question is out of topic. So from your explanation, this compound here is important, and also there's like different paths and reaction mechanism to synthesize it. So my question is, what is the consideration for the effectiveness of reaction from an industry perspective? Is it the quicker one, or based on the number of the yields, or depends on what compound we would like to synthesize? Thank you.
Thank you. So there's a lot of consideration for industry in terms of this chemistry, or any chemistry, by the way. So industry would love to have the highest yield. Yeah, we need to have something that is very high yielding. Number one. Number two, we want something to be done very quickly. So the turnover is very quick. If I can have a reaction in 1 minute, why do I need to have it in 1 hour, right? So the turnover is very quick. So number two, so yield and reaction time. Number three, reaction conditions. So reaction conditions, industry prefer to have reactions that are done at room temperature, so they don't want to spend energy. Yes, they don't want to spend energy on heating or cooling the reaction. So room temperature is really good. Industry would like to have reaction done in water because they don't want to deal with organic solvents. Now, dealing with organic solvents, first of all, they are more expensive. Another thing is that they become as an impurity, and you have to make sure that they are out of your product. So if you have a little bit of a product, a little bit of water in your product, it is probably fine, okay, because water can be moisture, right? Another thing is that you want to have a product that is clean, so that you are not going to do purification such as a crystallization or chromatography. Another thing is that you want to do reaction with reagents, or the catalyst is either cheap or no catalyst at all. If no catalyst, that is perfect. If your catalyst is cheap, this is a preferred. If your catalyst is expensive, then it should be recycled. Yeah. Industries would like to do or would like to avoid the use of metals if possible, because metals can sometimes leave traces in the compound. And if you have a trace metals in the compound, then it becomes a problem for the use of the final product. You need to have a lot of purification to get rid of the metals. Industry would like to use starting materials that are cheap, starting materials that are sustainable, and industry would like to actually also use materials that don't have toxicity, right? I don't have to have toxicity. If industry would like to use something like solid, not something like liquid, because it's very easy to use solid, to transport solid. It's very easy to store solid in comparison to liquids. So these are the general requirement for industry to have for a reaction. Yep. One more is industry would like to also use one-pot reaction. What is one-pot reaction? If your reaction is a few steps, we can do all these steps in just one container. So you add A to B, it gives you C, and then add D to C, it gives you E, then add something to E, it gives you the final product. So this is called one-pot reaction, right? Kahya, is that does that answer your question?
Yeah, it's answer my question. Thank you, sir.
Thank you. All right, we have Sarah.
Okay, thank you, Prof, for the opportunity. I want to ask from the application for the synthesis of NSAIDs and anti-tuberculosis lead compound. From the picture, it says the X are N or S. Is there any reason it has to be N or S, or it can be any other element?
So our X here, what is there in the literature? It is either a nitrogen or sulfur. A nitrogen or sulfur. Of course, so this work has been presented in the literature, and the reference for this work is here. All right. So these guys have screened different compounds, and they found that the compounds in which X is either nitrogen or sulfur are having higher bioactivity in comparison to compounds if this one is, for example, carbon, right? So I don't know what type of evidence they have, but usually this is, for example, is done using docking studies. So molecular models, computer models you use, and you take this structure and you dock this one in the protein and see the interaction between this center and the protein residues. So you probably have interaction between the nitrogen here, for example, and some of the hydrogen on the protein residue. So probably it's a hydrogen bonding, for example, between the nitrogen and sulfur and the hydrogen that is present in the protein. So that's basically what I can tell you. So the biological study, their biological study revealed that nitrogen is good, sulfur is good. I am not too sure what evidence they have, but I suspect that it's probably because of hydrogen bonding that you always get when you have nitrogen and sulfur. This ring here is a flexible ring, right? It's a flexible ring, so it's not something that is really solid. So I think it's most likely it's a hydrogen bonding that is present between the nitrogen and the protein. Sarah, does that answer your question?
Okay, thank you so much, sir.
Good, thank you. We have Hassan.
Okay, thank you so much for your chance to ask, Professor. So for my question is in the slide, in the page 71, synthesis of tetrahydroindoles past works. Okay, so in the last line, I realized that the last phase is to reduce the ketones group by using sodium borohydride.
Yes.
In order to remove the ketone group. So my question is that I realized that sodium boron hydride is a mild reduction agent.
Sure.
Can we use a stronger reducing agent such as lithium aluminum hydride or maybe PDC as a more considerable reducing process? Thank you.
Right. You're absolutely right. So you can use lithium aluminum hydride, but remember, lithium aluminum hydride is a stronger reducing reagent, and also it is much easier to deal with sodium borohydride rather than lithium aluminum hydride. Sodium borohydride, as you said, is a milder reagent. Lithium aluminum hydride is a strong reagent. If your solvent, for example, methanol, if your solvent has a trace amount of water, then lithium aluminum hydride will catch fire. Sodium borohydride is fine. It's not that strong. Okay. Sodium borohydride usually doesn't reduce ketones, but because this ketone is somehow special, it's next to an aromatic ring. And because of this next to an aromatic ring, therefore, this is like an activated one. All right. And then it reacts with the sodium borohydride to give you the product. Hassan?
Okay, thank you so much, Professor.
All right, Hassan, thank you. So we have Anida here.
Hello, sir. Sorry, I had trouble before.
That's
So
okay.
my name is Anida from SKOB Group 4. I want to ask question the material in page 65. Okay. In the slide, it shows that our site, which is R1, R2, and R3. So the question is there any requirement for the groups that can fill the position of the R1, R2, and R3?
So there are basically no requirements. Okay, so there is no requirement for R1. There is no requirement for R3. Okay, there is also, so is there a requirement for R2? R2, as long as it is an alkyl group or aromatic ring, it is basically fine. So there is no kind of special requirements for these groups. You can use any group that we have. So for this kind of chemistry, we don't have requirement. Sometimes in the previous lectures I gave, I mentioned that there are some examples in which if you have R3 as aromatic ring, then this reaction doesn't work or the yield is very low. But in this case here, if R3 is aromatic, as you can see here, then the reaction work, we don't have a problem, right? The reason is that because if you have an aromatic ring here, so you have, so if we have this, this is our aniline, yeah? So aniline is basic. However, it is less basic than this one and this one and this one. And this is because your lone pair of electrons can undergo resonance. This can come here, and these electrons can go on top of the carbon. So these electrons are really busy doing resonance, and therefore they are not so much available. That's why this becomes less reactive. But in this case, we are lucky. You can easily obtain the product. Anita, does that answer your question?
Yes, thank you, sir.
Okay.
Prof. Zahir, many questions.
Yeah, I like
yes.
this group. This group is like
Yes.
automatic. They have very good questions, one line after another. This is really good. I like this.
However, because of the time limitation, could we proceed to one question from you, maybe, to the students before we close?
Right.
Yes.
So I think this question is very easy for this group. So this is the question: if you can make this.
Okay, the student can note it. And what starting material needed to synthesize this?
Exactly. What is the starting material that you need to make this? So you have to go for retrosynthesis exactly what we explained before, right? So I can give you a clue. So this is one section, right? This is another section, all right? And this is another section all the way here. I think I have helped you to get the answer.
Okay, maybe one or two students want to answer.
Yes.
Yeah, because we have a bonus, a point bonus. If
Bonus
anyone,
point. Okay.
yeah, if
All
anyone
right.
can answer
The
correctly.
first person to get the answer will get the bonus point. Anyone who can contribute? Anyone who can suggest something?
Yeah, anyone? Maybe. Okay, you can choose product 1 or product 2.
Let's go for product 1 maybe first.
Okay, product 1.
Let's go for 1 first and see how you guys do.
Okay, product 1. Anybody want to answer? And also welcome to this meeting, Dr. Asep Saifullah.
Yes.
Good morning. Thank you, Dr. Bayu Ardiansa. Good morning. Nice to meet you again, Professor Jahir today. Thank you
Prof. Asif.
for this lecture. It's very interesting.
Thank you so much. Thank you. Thank you.
Okay, students maybe still
yes,
still thinking, still study.
That's okay. I think it will.
Okay, maybe the question product 1 and product 2 we can use for the homework and also material to be prepared for midterm tests. So because of the time limitation, so sorry.
That's okay.
Yes. Yeah. Here today is the last section of the organic chemistry lecture series in the UI Resolve program held by the Department of Chemistry, Faculty of Mathematics and Natural Sciences, University of Indonesia. So many questions and discussion from this meeting. It is really good for our student at UI, and we thank you very much, Prof. Zahir. And today we have Dr. Asep Saifullah as the head of the Department of Chemistry. He will officially give some remarks. So to Dr. Asep Saifullah, the time is yours.
Okay, thank you. Terima kasih, Pak Bayu. Good morning, everyone, the student who participate in this lecture series. I would like to express my gratitude and high appreciation to Professor Dr. Jahir today from Nanyang Technological University of Singapore for his kindness and his great time with us, to involve and give a very insightful lecture in this UI resolve program. So I found that really this resolve program is very important and very beneficial for student. So the student could get the first-hand information, data experiment from the world-class professor from Nanyang Technological University. So from this lecture entitled Cascade Conversion of Carbohydrate to Pyrrole and Indole, Pak Bayu, student should realize that the knowledge that Professor Jaher Jude has shared with the student are the knowledge that come from the research, and data from research has been validated, verified. So the empirical data from the experiment now become knowledge. So I hope that students get the wisdom from the professor, so the student later on will use this knowledge and wisdom to follow the path of scientists in doing patient experiment in the lab for his final project and their future career. Again, thank you very much to Professor Jaher Jude from me and on behalf of Department of Chemistry, Universitas Indonesia. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Salam. Thank you very much, Dr. Asep Saifullah, as the head of department. And as a token of appreciation, we will give the certificate of appreciation. So, Mbak Safira, could you please? Oh yeah, I'm sorry, Prof. Zahir, could you unshare? Yes.
Yes.
Okay, this certificate will be given by Dr. Asep Saifullah. Pak Asep.
Okay, thank you, Pak Bayu, to Professor Dr. Jaher Jude. Yeah. We would like to give you a certificate of appreciation in UI result as a world-class professor lecture series in the topic of cascade conversion of carbohydrate to pyrrole and indole. Yeah, in appreciation of his enduring commitment to providing excellent knowledge in this program. Again, thank you very much, Professor Jaher Jude.
Thank you.
Okay, thank you very much. Ladies and gentlemen, finally we come to the end of the lecture series. So I would like to say thanks again to Associate Professor Zahir Jude, to Dr. Asep Saifullah, and Dr. Muhammad Ridwan, who and also to students and other participants with very active participation and also discussion in this lecture series. Hope the knowledge and also the material will be beneficial for everyone. So finally, I will close this program. Thank you very much, everyone. Assalamualaikum warahmatullahi wabarakatuh.
Thank you so much. Thank you. Waalaikumsalam. Thank you so much. Thank you.
Terima kasih.
Thank you so much. Thank you.
See you again later, Professor.
Inshallah,
See you
jazakallah khair.
again.
Thank you so much. Thank you.
Please keep
Assalamualaikum.
in touch with us.
Inshallah, inshallah,
Please
inshallah. We
keep
should,
in
we
touch.
should.
Yes.
Inshallah,
Assalamualaikum
inshallah.
warahmatullahi wabarakatuh.
So
Yes.
there's something that I would like to send you. I
Yes.
don't know if this is gonna happen or no, but NTU has something called the COIL program.
Okay.
So COIL program allow us to share a full module with your students.
Okay.
So this full module, so I teach a course on a drug formulation. So I think this will be really good for chemistry students.
Okay.
So this module NTU allow us to kind of teach a full course. This course is in collaboration with your university. Any student can join from the chemistry department or any department to join together with our students. So the idea here is to make sure that there is a good discussion between students with different cultures. Students enjoy learning together. I think majority of this course will be online. So majority of this course will be online. Students are allowed to have, they will have access to my lectures, they will have access to my notes, and there will be a kind of an exam. Yeah, so this is what NTU is providing. So there is a grant call right now happening. I don't know when it's going to finish, but I can dig that one up. I don't know if you are interested in, and I don't know if the university, I don't know if we are going to be selected, but maybe it's something that is good to try. So the cost for this, it doesn't cost you anything. I think there's no cost for you.
Great to hear, Professor.
Good to hear.
Dr. Ridwan and Dr. Bayu must be very happy to know about that.
Yeah.
So, yes.
So there is no cost involved in this. NTU will take care of the cost of this program. So there is a proposal to be written. Maybe we just need the help in writing some sections of the proposal.
How many students allowed to participate, Professor?
Sorry?
How many students who can get involved
So
in
there's no
this
limit.
program?
There's no limit on the students.
Okay.
There's no limit on the students. So the idea here is just to make sure that the students talk to each other and they do some kind of discussion and project together. So this will be really helpful to have this cross-culture thing. That's what this will be helpful to.
Okay.
Yeah.
When will it be held?
So usually I teach this course in August.
Okay.
From August till November.
Okay.
This is the usual time I teach this course. Yeah.
Okay, Professor, is it this class? Is it can be the grade can be given to our students? I mean, the grade will be issued if they get like A or B or C. Can we?
Yes. So this is a full course.
Full course, right?
It is a graded course.
Graded course. Okay.
It has exams. It has assignments. It has everything.
Okay.
So this is not just like for general knowledge. Yeah.
Yes. So we also have that kind of program. I mean, we have like a kind of student exchange, even though it's online course, but we can do that one. And we are very pleased to hear that information from you.
Yeah. So let me figure out more, and inshallah, I will try to see more information and see if we can apply for NTU to support this course. There is so if this course is accepted, there will be a trip from NTU students coming to see you and see some industry and talk to the students, just like, you know, some sort of a trip will happen. But this trip will be supported also by the NTU.
Ah, great. We will we will follow up that one for sure, Professor. So
Inshallah,
maybe
inshallah.
we will email you, inshallah.
Inshallah. I will let you, inshallah, know. I'll let you know the details, inshallah, and see how we can process this one, inshallah.
Okay. Thank you very much.
And UI is on the list of the universities that we can apply for.
Oh,
so yeah.
Alhamdulillah. Alhamdulillah.
Yes. Alhamdulillah.
Okay.
Good.
Okay. Thank you very much,
hear.
Professor.
Jazakallah khair, inshallah.
Thank you.
Inshallah.
Jazakallah. Jazakallah.
Thank you so much, Dr. Bayu. Bayu is a very good organizer.
Yeah, he is.
Of course.
Thank you so much. And I just hope that the student got an understanding of not just the chemistry, how we do research. That's really important.
Yes.
Thank you so much, Dr. Asif. And Dr. Ridwan, thank you so much. I still remember the lunch we had together was very nice lunch. But now we are fasting.
Okay.
Okay.
Thank you
Thank
again.
you. Assalamualaikum.
Assalamualaikum.
Mas Bayu.
Ya, Pak Ridwan, terima kasih. Pak Asep, Pak Ridwan.
Terima kasih banyak. Saya izin live ya.
Ya, sama saya juga. Ya, mahasiswa ini terima kasih nih udah partisipasi. Nah, belajar yang benar ya. Terima kasih, Pak.